What's up, my chemistry students? Today we are going over Hess's Law. Hess's Law is one of my favorites because it's like dealing with puzzles. If you like math and you like substitution and solving equations, you should like Hess's Law. If you don't like it at first, hopefully you'll like it after you do a few problems. Alright, so let's talk about Hess's Law. I'm going to give you an analogy first. And this is I think, an old Chinese proverb. Says, there are many paths to the top of the mountain, but the view is always the same. Okay, so it doesn't matter how you get to the top because everything looks the same from the top. All right, you don't need to write that, by the way. All right, so let's say here's Red. She's going to Grandma's house. Doesn't matter how she gets to Grandma's house, just as long as she gets there. So she could take this path, a little zigzag path, and then a steep climb at the top. She could do a really steep climb, go straight up, it's the shortest distance, or she could take the path I would probably take. Actually, I would not be climbing this mountain, which is a gradual climb. And so, it doesn't matter which path she takes as long as she gets to Grandma's house. So, a couple of other ways this can be written for Hess's Law, and it is that the heat evolved or absorbed in a chemical process is the same whether the process takes place in one step or in several steps. So it doesn't matter how much steps it takes to get there, the amount of heat is always going to be the same. And so if I have this reaction here, to get from here to this product here, it's negative 890 kilojoules if it's in one single step. If it were in two steps, I could have some what we call an intermediate, and this would have this amount of energy released, and this would have this amount of energy released, but if you add them together, they'd be the same. All right, another way to say Hess's Law is if two or more chemical equations can be added together to produce an overall equation, the sum of the enthalpy values, sum of the enthalpy equals the enthalpy change of the overall equation. Now, this seems a little confusing, but once you do a few of these, this will make sense. Okay. All right, so here's how we're going to use Hess's Law. So a bunch of steps. Number one, the goal is to obtain the desired reaction by adding up two or more reactions, which is kind of what I just said. So we're going to take at least two reactions, turn them into a desired reaction. We're going to work backwards. So for each reaction, we'll line up the reactants to the desired reaction. So we're trying to make it look like the desired reaction by lining them up in the correct spot. If it's a reactant in the desired reaction, then we want it to be a reactant in the equation that we're working with. If we have to change it, if it's not already lined up, what we'll do is we'll flip the equation by multiplying by -1. I'll show you. That'll make hopefully more sense later. If you have something that is a reactant or a product and it appears more than once in a reaction, so you see it all over the place, do not mess with it. Leave it for the end and usually just cross your fingers that it will work its way out. So you won't have to deal with it, and if you move everything else, then hopefully it'll balance on its own. All right, and then the last step here is make sure that the coefficients match. If they do not match, we're going to multiply the coefficients of the entire reaction by the necessary number. Sometimes this is a fraction, like a 1/2, 1/3. We will also need to multiply the delta H value by that same number. Okay, like I said, this will make sense more when we start doing these problems. All right, 5, always write down the state symbols. Don't be lazy, skip writing solid, liquid, gas, aqueous, because some problems will simply ask you to just cancel out certain states. Okay, so make sure that you are still writing all of the states. You're going to cancel out substances that appear on both sides of the arrow, so where it's a reactant and where it's a product on both sides. And the last thing, on occasion, there will be multiple steps that you'll have to do in order to finally solve this problem, this puzzle. Okay. Let's try one. So it says determine the heat of reaction for the reaction. So this red reaction here, this is our desired reaction. This is what we want to obtain by using these 3 reactions below. I could have 2, I could have 3, I could have 5, I could have a bunch. All right, so then what we'll do, and I would like you to color code this with me, either with a highlighter or just a crayon or some other system that you use so that you can see what I'm doing here. So you can go back to your notes and see. I suggest highlighting them. So we're looking at C2H4. Oh, here's what I said to do. It says, first, check to see if they are lined up, then check your coefficient. So what I mean is, if it's on the reactant side in the desired reaction, is it on the reactant side in the final reaction, or the reaction we're trying to manipulate? All right, so color code C2H4. I'm going to color code mine red. You might highlight it yellow. Okay, and I'm going to find C2H4 in the equations below. It's right here. Okay, is it on the correct side of the reaction? Yes, it's a reactant, and for the desired reaction, we want it to be a reactant. Great. And is it anywhere else? No, just right there, C2H4. H2. So let's highlight that. I'm making that one green. Okay, so where is H2 in here? It's right there. So it's on the left side. Now, it doesn't matter the order that it's in. It just matters that it's a reactant. It's a reactant on the desired reaction. It's a reactant in the reaction I'm manipulating. Okay. The last one is C2H6. Okay, where's that in here? That is right there. Is it on the correct side? No. In the desired reaction, it is a product, and in this reaction, it is a reactant. So what we're going to do is we're going to flip this equation. We're going to flip the entire thing by multiplying by a -1. Okay, so write parentheses around the entire equation and write times -1. So don't forget to times -1 here. You have to show this. Okay, so then what we'll do is we will rewrite this reaction. So rewrite it, even the ones that were not changed. The one that got flipped, which was the second reaction, notice that the products are now on the reactant side and the reactants are now on the product side. The other thing that changed, when I multiplied delta H by a -1, it turned the negative that was there before, see it was negative right here, it turned that into a positive value. Great. Another thing that's helpful when you're writing these is to line them up so that the arrows are pretty much lined up and that your delta H's are kind of lined up. All right, so then what we'll do is we're going to start canceling things that are on the product side and on the reactant side. Okay, it's almost like you're subtracting them. All right, so here we go. We've got CO2 on this side and CO2 on this side. The coefficients match and they're on opposite sides of this arrow. So that cancels with this. All right, next, what do we have? So we have O2. So we have 3 O2s here plus a half O2 here. So we have 3.5 oxygens on the reactant side. All right, let's see how much we have on the product side. It says we have 7 halves. 7 halves is 3.5, so that cancels. Okay, you could try subtracting to see. So like 7 halves minus a half would give you 6 halves, which is 3, and 3 minus that 3 is 0. So they all cancel. All right. Next, is there anything else that cancels? Anything else that is on the reactant side and on the product side? Well, there's water. All right, so here's 2 waters here and 3 waters there. Oh, we also have another water here. So on this side, we have 2 waters canceling out with these waters. That would leave me with 1 water. which would cancel out this water. So 3 waters here and 3 waters on the reactant side. Okay. Then you're going to write the overall equation. The overall equation is everything that's left over that has not been canceled. So you're just going to make sure that they stay on the correct side. So C2H4 stays on the reactant side, H2 stays on the reactant side, then we draw our arrow. The only thing on the product side is C2H6, and then delta H is negative 137 kilojoules. All right. We're going to calculate this one. So we're going to use these 3 equations. Notice this one has this little symbol here. This is delta H standard, and so this is happening at thermodynamic standard conditions, which is 25 degrees Celsius and 1 atmosphere of pressure. Okay, so a little bit different standard. Way to write standard for us. All right, so let's see. We've got these 3 equations. Again, I want you to color code them. So carbon. Where is carbon? Carbon's right here. Is it on the correct side? Yes, it's on the reactant side. Great. Does it have the correct coefficient? No, it has just 1, and we want 6. So we're going to multiply this entire thing by 6. Okay. All right. Then we have H2. And H2 is on the reactant side here and on the reactant side there. It's just missing the correct coefficient, so we need to add a 6. O2. It's right here, and then it's here, it's here, it's here, which is all on the reactant side. But trying to get that coefficient to match is going to be way too hard, so I'm not going to mess with it. Because I see this oxygen in multiple locations, I'm going to leave it for the end and pray that it works out and I don't have to worry about it. Okay, then we have C6H12O6. That is right here. It's on the wrong side, so I'm going to have to multiply this. It has the correct coefficient, so I just need to multiply it by -1. Okay, so I'm going to take all those 6's and the -1 and I'm going to distribute them in. The -1, of course, just flips it, but the 6's will change the coefficients for everything in the reaction. Plus, it will be multiplied by the value of delta H. Alright, so I went ahead and did that. I added the 6's, changed the value of delta H by multiplying by 6. Okay, same thing here. This was a 1/2 before, so that was a 3. The last one, this one just flipped, and then the sign changed to a positive. Okay, we're going to add them, actually first, we're going to cancel out things that are on opposite sides of the arrow that are the same. So let's see, first thing, O2. I've got O2 here, 6 of them. I also have 6 O2 there. I don't really need to add these 2 first. Let's just cancel these 6 with these 6. Still have these 3 left over. Okay, next, we're going to cancel out the CO2. So we have CO2 here and 6 CO2 there. Okay. And then we're going to cancel out the waters. I have 6 waters here and 6 waters there. Okay, they're on opposite sides of that arrow. And then we are done. So what's left over? We have 6 carbons, 6 hydrogens, 3 oxygens left, and 1 glucose. And then we'll add these together. Okay, so that should come out to be the same. Here, again, we're looking at decimal places for significant figures. 1, and that's the original amount of decimal places. Okay. One thing that I forgot to mention is you should go back to see that this equation, this overall equation, matches the desired equation, and this does. This is actually the desired reaction that I was looking to obtain. Okay. All right. I want you to do this problem just in terms of what do you multiply each one by. So don't solve it. Do this on your own. What are you going to multiply each one? Okay. Great. So you should have seen that you had sodium here and our reaction has 2. So you would multiply it by half to get 1. And then for the chlorine, it has a half, and it's a 1 here, so we'd also multiply that one by a half. Okay. Notice it also has sodium chloride. Oops. Okay, and since it's in this same equation as this one, multiplying by a half also changes that to 1. Alright, so I really like these problems. They are like solving little puzzles. I hope that you like them too and that we can do enough practice with them. See you next time.